Hello everyone. In today's lectures, I will be discussing on the block ciphers. So, as we know, block ciphers takes a block of plain text bits and generates a block of ciphertext bit. Or we can say a block cipher is an encryption method that applies a deterministic algorithm along with symmetric keys to encrypt a block of text rather than encrypting one bit at a time as in stream ciphers. I have already discussed about the stream ciphers. In stream cipher, I covered uh, general structure of the stream cipher and linear feedback shift register, attack on linear feedback shift registers, and the stream ciphers based on linear feedback shift register. So in today's lectures, I am discussing on block ciphers. So the general structures of the block ciphers is given in this figure. This is the figure of the block cipher. This is the general structures. In this, we have this is a black box. This is the block ciphers. It takes n bit inputs of plain text and the k bit keys, and the output is n bit ciphertext. Or mathematically we can say this is a function, this is a function, this is a function e, function from n bit plain text which takes the input of n bit plain text, k bit keys, and the output is n bit text. So an R round n bit block ciphers is a block ciphers in which there are R round inside it, and the size of the plain text block is n bit. So this is the structure of R round n bit block ciphers in which there are R round. This is the F1 is the first round, F2 is the second round, Fr minus 1 is the R minus 1th round, and this is the last round, Rth round, Fr. So in the first round, the X naught is the plain text. This X naught is the plain text which is n bit size plain text, and K1 is the first round key, K2 is the second round key, and Kr is the Rth round keys. These round keys are generated by a key of size k bit, which is called the effective key. So all these round key K1, K2, Kr, these are generated by some key scheduling algorithm. The X naught is the input plain text, and X1 is the output after the first round, so which is the function of this X naught and K1, and this output of the first round goes into the second round F2, and the output of the second round is X2, which is a function of X1 comma K2, and similarly the ciphertext which comes out from the Rth round is Y, which is the function of F XR minus 1 and KR. So this is basic structures of R round n bit block ciphers, and the decryption of the block cipher is same as the encryption of the block cipher but in the reverse order. So here this is the decryption. That means we take the ciphertext as the input, and the ciphertext goes to the Rth round with the key Kr of the Rth rounds. Then this output of this round goes to the next round, and finally after the F1 we get the plain text X naught. So this is the same as the reverse process of the encryption. So there are three type of modern block ciphers. One is the substitution and permutation. One is called the substitution and permutation network, and second is data encryption standard, DES. In DES there are 16 rounds and the block size is 64 bit, and the size of effective key is 56 bit, and the size of each round key is 48 bits. And the third one is advanced encryption standard, which is also called AES. So there are 10 round AES, 12 round AES and 14 round AES. There are three variant of this AES, and the block size is 128 bit. So the rounds number of round depend on the number of key. If there are the 10 round AES, then the key size is 128 bit. If it is a 12 round AES, then the key size is 192 bit, and if it is a 14 round AES, then the key size is 256 bit. So now come to the DES block ciphers. So a DES block cipher is a fiscal cipher or a fiscal structures. A fiscal structure is shown in this figure. This is the fiscal structures. In the fiscal structures, the plain text block is divided in two parts, two half parts, L0 and R0. And so it's suppose we have this plain text box. Sorry. If we have this plain text block L0 R0 not, then this R0 goes to some function f. I will discuss this function. This is called the DESF function, and some first round key K1 is applied on this function f1, and the output of this is XORed with the left half part, and this output of this XOR is the right part of the second round input R1, and this L1 is this R0. So this is the fiscal structures of round 1. So here this R1, here this R1 is L1 is the same as R0, and R1 is L0, this XORed with F of R0 comma K1. Okay, so this in DES, so all these rounds are the fiscal rounds. So there are 16 fiscal structures in DES. This F1, F2, F16, these are the 16 fiscal structures, and the key size is 64, and the key size is 64 bit. Sorry, the plain text size is 64 bit, and the key size, effective key size, is 56 bit, and the size of round keys, these are 48 bit. So this is the one function f capital F1 of the DES1 round. So now if we come to the two round fiscal structures, we will show that decryption decryption is easy in this fiscal structures. So this is the two round fiscal structures. So in this in the first round, L0, the block is divided into two half part, L0 and R0, and the first this L1 and R1, these are the output of the first round, and L2 and R2, these are the output after the second round. So this L1 is R0, and this R1 is this L0 plus this f of R0 comma K1, and the R2 is this R2 is the R1, and L2 is the R1, and R2 is L1 plus L1, this XOR with f of R1 comma K2. So now if we come if we want to get the original plain text L0 and R0 from this L2 and R2, then first we will get the intermediate text, this L1 and R1. Then after that we will get L2 and R2 from this. So the formula is given here. So this R1, so this is given that R1 is this R1 is the L2. So this R1 is L2, and from equation 1 we can see that, from equation 2 we can see that this L2 is equal to this R2 plus f of R1 comma K1. And since we know that this R1 is the same as L2, so L1 is R0, which we already knows, XORed with f of L2 comma K1. We already know L2 and K2, so we get L1 and we also get R1. So we get the middle text L1 R1. Now we will find L0 R0 from this. Since this R0 is L1, from here, from equation number 1, and L0 is equal to this R1 plus f of R0 comma K1 from equation number 1. So L0 is equal to this R1 plus f of L1 comma K1. So we get L0 and R0 from the ciphertext. So this is about the crystal structures. So these crystal structures are the component of the DES ciphers. So now I stop here. So I will continue the DES ciphers in the next lectures. Thank you.